Okay, thank you very much, Sarmistha. And thank you, everyone, for sharing your time here. I hope you're having a good afternoon. Here it's shaping up to be a fine morning. I am, in fact, going to talk about what the Neutron Star Interior Composition Explorer, which is one of NASA's missions, it has told us about dense matter and also the exciting prospects for what it will tell us in the future. And here, on the bottom left, we see a representation of NICER aboard the International Space Station, where it has been competing with various things, including an experiment to see how paint dries in space. The hope is that NICER's results are more interesting. In the bottom right, I'm showing the people who are, in fact, the stars of this particular movie. These are the people who made NICER. They actually constructed it in the laboratory, and it has worked extremely well indeed. Now, the outline here, I don't know that I'll have to convince you, but I'm going to discuss first the importance of neutron star radii, why measuring radii with both precision and, importantly, accuracy is going to be extremely important going forward as we try to understand the centers of neutron stars. And then I'll talk about the published NICER measurements of mass and radius of this particular neutron star. I'm going to talk only about the work that we did in our group. This is the paper Miller, Lamb, Dittman, etc. in 2019. This is a work in which we present our measurement of mass and radius for this neutron star. We talk about the equation of state implications, and we also talk about the implications of the spot patterns that we are inferring. But I also encourage you to read the papers from the other group within NICER that did independent analysis, who broke those three categories into three separate papers. The key point in terms of a comparison is that the favored models for these two independent groups are fully consistent with each other, not just in the inferred mass and radius, but also remarkably in the spot pattern. As Sarmistha said, please feel free to type your questions in the chat window at any time, and I will pause twice during the talk to determine whether anyone would like to pursue discussion points. One just before I talk about the NICER results themselves, and one just before we go to the implications for the equation of state. I don't know if you've read these papers, and I don't want to keep you waiting. I'll give you, therefore, first the main results. This particular pulsar rotates at a little bit more than 200 hertz. This is an isolated pulsar. This means that we did not have any information from radio timing of the binary to give us, say, the mass or the observer inclination. What we find is that in rough measure, the equatorial radius is about 13 kilometers plus or minus 1 kilometer, and we also were able to find the gravitational mass to about 10%. The best configuration we find has 3 spots. By best, I mean in a Bayesian evidence sense, but there is a very close approximation to that evidence for a 2-spot configuration. Something that is remarkable and was a surprise to a lot of people is that what our work found, and the other group as well, is that all of the spots are in the rotational hemisphere opposite us, the observer. We hope this means they're not social distancing from us. We think that this is because of the complex evolution of a magnetic pattern of a millisecond pulsar. In addition, at least one spot is highly elongated, meaning that this is definitely not circular. Why are radii particularly important? We know that we can measure various things about neutron stars, and as Jim indicated, for several neutron stars, we have quite precise masses. For cases in which there is a binary neutron star system, and one of them appears to us as a pulsar, the precision has been better than the 0.1% level in a few cases. That's not true for the highest measured masses, but we still have pretty good estimates. But as we see here on the right from a paper in 2010 led by Paul Demarest, even if you take the selection of particularly proposed equations of state, which satisfy the constraint that you have to be able to sustain neutron stars of at least the highest mass yet seen, well, you still have a wide range of possible radii at whatever mass you wish to measure. You'd love to be able to measure the radius, but this is tough. We can compare this. The masses have an effect at a distance, Kepler's laws plus a few other things. The radii do not. And therefore, you end up with greater model dependence. And this has led to an interesting factor, which is you can look through the literature over the past 10 to 15 years, and you'll see a number of papers where there is an estimate of the radius of an individual neutron star that is quite precise. These answers may even be right. However, they are susceptible to a huge amount of systematic error. And in just a minute, I'm going to give you a particular example of how that can come in. The work done with the NICER team can help a great deal, essentially because it gives us extra information. Now, before going to my example, I want to put the error ellipse here. This is what we get for this J0030 neutron star. And as you can see, this 68% ellipse spans a lot of radii. However, it's obviously a step. It's something that tends to favor the ones in the middle. And as time goes on and we accumulate more data on this pulsar and other pulsars, this is something which is going to give us tremendous extra information about neutron stars. I mentioned systematic errors. When we think about the X-ray based neutron star radius measurements that have come from various communities, these have typically focused on one of two cases. One is a quiescent star, which is believed in the past, say the past tens, hundreds, or thousands of years to have actively accreted. These are called quiescent low-mass X-ray binaries. Essentially, what you want to do is measure the distance, the flux, and the spectrum. From this, you would like to be able to get a reasonable estimate of the radius. The other, as Jim mentioned, is from thermonuclear X-ray bursts. In both cases, you are relying strongly on fit of the spectrum. But there's a significant problem with this, at least potentially. The typical assumption made in those analyses is that you have a surface which radiates uniformly with the same effective temperature everywhere on the entire surface. Part of the assumption, implicitly, is that if it were not like that, you would get some hint. For example, you might have pulsations if you have a non-axis symmetric temperature variation. In fact, you do see pulsations in many thermonuclear X-ray bursts. But there's also the assumption that even as a function of latitude, there's no temperature variation. The question is, would you be able to determine if there were? And the answer, unfortunately, is no. Here we have an example. I constructed synthetic data using a local emission that is a black body everywhere. In reality, it isn't, but we're doing the analysis this way. And I had a huge variation, a temperature that varied smoothly from KT equals 2 keV at the equator to 1/10 of that at the pole, a giant range. And yet, I fit this assuming a single temperature. What you notice here is that if you look at the chi-square per degree of freedom, 181 over 173, that's fine. That's no problem. You would never have a hint that you have a terribly wrong model. But even worse is that although I used 12 kilometers for the actual radius, the fitted radius was less than that. But look at this uncertainty. If we just use this fit, we have tremendous confidence in our roughly 10.5 kilometer radius, but it's terribly wrong. In fact, we're talking about many, many standard deviations off. So this is something that is a serious problem. We don't know whether the answers are right. We do know that we can have an apparently good fit and be very wrong in the statistical sense. This is ultimately the reason why many people have looked toward NICER as a way of getting more reliable answers, not just precise, but also accurate and therefore reliable. In particular, Fred Lamb of the University of Illinois and I have worked with our colleagues for many years to determine whether we have a similar problem with NICER-like data. The difference of NICER data is that you introduce not just the spectrum, but also the phase dependence of the waveform. You can think of this, therefore, as an energy-dependent waveform, or you can think of it as a phase-dependent spectrum. It adds a new dimension to the data. What we have found is that this minimizes systematic errors. By this, I mean we have generated synthetic data using models with different beaming patterns or spectra or spot shapes or temperature distributions than we use in fitting the data, meaning that we're using the wrong model. What is the result? Either we get a terrible fit, or if we get a good fit, we have found so far no significant bias. This is an important, really a critical aspect of the NICER analysis. And indeed, in much of the rest of the talk, I'm going to continue returning to this theme. It's not enough to have a precise measurement, you need an accurate measurement as well. The general idea that we apply is as follows. And here, by the way, I'm showing an image from the NASA press release related to the December 2019 publications. We suppose that neutron stars have obviously some glow, they're not at absolute zero, but that there are some hotter regions, which we can call hot spots, and these are radiating, and as the star rotates, we are getting different views of this. This is why we are getting a phase-dependent spectrum or energy-dependent waveform. We do Bayesian fits. That is, that we trace the rays from the hot spots on the neutron star surface with some assumption about the mass, the radius, the angles, the temperatures, the spot sizes, and so on. We compare that with the waveform and repeat tens or hundreds of millions of times for different parameter combinations until we get a final posterior. I mentioned that we want to think carefully over and over again about the possibility of having systematics come into our analysis. Fundamentally, what we are doing is tracing photons from the star to the observer. It would be lovely if we could assume that the star does not rotate at all. And this is because ray tracing then becomes extremely simple. If the star isn't rotating, the space-time is spherically symmetric. It is, in fact, the Schwarzschild space-time uniquely. Therefore, a given photon travels in a plane. So rather than literally needing to trace the ray from the star to the distant observer, instead we can say, well, we know it's a plane. We can calculate the total angle traveled very straightforwardly, and then we can figure out where it ends up. But these stars do rotate. 200 hertz is faster than I would like to rotate. So at that speed, you worry about other things. For example, frame dragging. There are papers that have actually claimed that frame dragging must be critical because frame dragging, recall, is first order in the rotation. You also have higher order effects. For example, the star is no longer spherical. The star becomes oblate. We therefore need to know what are we going to need to do. Because if we are required to take into account frame dragging in particular, even things perhaps like the effect of the oblateness of the star on the space-time, well, then we've got a major computational task, taking 10 to 100 times longer per ray than it would be if we could assume a Schwarzschild space-time. But fortunately, frame dragging does not matter in any significant way for the stars that we are analyzing. This is a figure from one of the support papers that was released in December of 2019, led by Slavko Bogdanov. And this is for a star of 200 hertz, like our J0030 pulsar. And what we see here for particular assumptions about other parameters, we have the solid line is what you might call numerically exact. It uses the RNS, or rotating neutron star code, to solve everything properly. Assuming you have uniform rotation, meaning like a solid body, you find that you're solving for the external space-time, the exact shape of the star, everything. And remember, by the way, the external space-time to a rotating neutron star is not the Kerr space-time. You have to solve for that numerically as well. Very time-consuming. But then we compare this with two different approximations. One, the so-called Schwarzschild plus Doppler, which Fred Lamb and I introduced in 1998. We assume the star is spherical, the external spacetime is Schwarzschild, but you do all the proper special relativity to trace from the moving surface to then the observer. The OS, this is the oblate Schwarzschild, introduced by Sharon Morsink and her colleagues in 2007, where you have a good approximation to the true shape of the star, so it's oblate, but you use a Schwarzschild external spacetime, and you do put in special relativity. Now, what we see here are residuals. This is the fractional difference in percent, and even the Schwarzschild plus Doppler isn't too bad. It's only off by 1.5% at most. But you can see that once we introduce the oblate shape of the star, even though we're keeping the external Schwarzschild spacetime, we have tremendous accuracy of the waveform. And it's worth thinking a little bit about why this is. Again, there are papers that have essentially done rotational order counting. Frame dragging is first order, oblateness is second order, and if that's all you do, you think frame dragging is more important. But two things. One is that the coefficient matters too, and it's a tiny one for frame dragging. And second is that, for example, when you think about the image of a black hole horizon, what you find is that frame dragging matters, but what it matters is it shifts the apparent location of the image. The shape is changed only to second order. Something similar might be happening here. Luckily, this means that the precision we need, we can treat the space-time as if there is no rotation. Another aspect of rotation was raised by Shantanu earlier in Jim's talk. And this is, we are using the Tolman-Oppenheimer-Volkoff equation. This assumes zero rotation. However, the stars we are examining are rotating. Their equatorial radii are therefore changed compared to what it would be if these are in fact not rotating. We might worry, therefore, that in our mapping, where we're trying to eventually get to the equation of state, we might make some errors. However, as this figure also generated by Sharon Morsink shows, this is not a problem. Here we have 4 different equations of state, which are basically going from soft to hard. And we find that at any radius any mass you would care to choose, the radius change from no rotation to 200 Hertz is negligible. We wish that this were the limiting factor in our analysis. Therefore, we are in fact fine in making the assumption of no rotation when we're mapping between mass and radius and the equation of state. With this in mind, I'd now like to tell you about some of the models that we used in our FITs. First, we consider uniform temperature spots. The spots can have different temperatures. They can be anywhere on the star, but we assume that these are uniform temperature. At first glance, you might say, this is ridiculous. Of course, the spots cannot be uniform temperature. There's no way you have uniform temperature and a sharp cutoff to the background. That's true. This, however, is where we go back to the work that Fred Lamb and I and our colleagues have done. Because of 2 basic things, one is that the beaming pattern is fairly broad, and the second is that gravitational light deflection spreads out the light. It turns out that you can actually do a fine job of modeling the emission and the energy-dependent waveform with a uniform temperature spot. We actually tried cases where the spots that we generate, the synthetic data, have a spread in temperatures, but it doesn't matter. We still are not biased in our fits. So that's something to keep in mind. We also allow the spots to be oval. We start with a circular spot and stretch or squash it azimuthally. This gives us, as it turns out, extra freedom that is useful in the fits. We include an unmodulated background as a possible component. This does not have to be a background that is actually stationary in time. Any background that does not vary in a way that is commensurate with the rotational frequency averages out over the millions of seconds of observation to be unmodulated at that particular frequency. So, background X-ray sources, local effects from the sun, instrumental noise, astronauts jumping around in the International Space Station. It all works just fine. We use 2 or 3 oval spots. We also allow there to be arbitrary overlap of the spots. You could have a hot spot on top of a cold spot or a cold on top of a hot. This gives us tremendous flexibility of modeling. We could have isolated spots, even things like crescents. If you have a spot that is hot and you have one that's very cold on top of it, that would give you a crescent. Now, the last thing that we did.
There are 2 questions.
Yes.
One is will the frame dragging and oblateness have no significant effect even for rotations higher than 200 Hz?
Yes, so good question. We can go back to this curve as one example. The effect of rotation on the equatorial radius is going to be quadratic in the rotation rate. For example, if you were to double this to 400 Hertz, then we would find deviations that are 4 times as large as this. But you see that even in that case, it's a very tiny amount. We're talking about something that might be a ½ kilometer difference, which is better than our current precision. So in that sense, we're doing just fine. When it comes to the ray tracing, even up to 400 Hertz, then again, the differences are insignificant between the true numerical answer and the oblate Schwarzschild. Therefore, in both cases, not only are we okay with this pulsar, we're okay with all the pulsars we're studying with NICER. Thanks for the question.
So a second question is, this is regarding I think this slide, that how do you do this calculation? Do you have modified matrices which include rotation, or do you do the perturbation theory on top of TOV?
This is not perturbation theory. This is something where you actually solve for real the vastly more complex equations involved when you have rotation.
The next question is, what kind of global B field configuration is giving 2-3 hotspots on one hemisphere? Or are these related to local B field concentrations?
These are probably related to local B field concentrations. As we'll discuss a bit later, we have no reason to expect that a star like this is going to be a centered dipole. Also, when we think about elongated spots, it's possible that the model is actually representing 2 close-by spots. So we don't exactly know what this is. It's likely that there are higher multipole configurations than the dipole, which are coming in, and that the return current and the radiation coming from the high-speed particles produced in the pulsar mechanism, this is what's heating the surface. So this is probably coming to local concentrations of the field. Shall I move on then?
Yeah, please move on.
Okay. One other thing to consider here is, as we increase the complexity of our models, we have to keep in mind the possibility that our sampling algorithms maybe aren't complete. We worry about that. And therefore, one of the emphases of our paper is on fits to synthetic data. In the case where we know we have the right model, are we getting answers that are consistent generally with the input information that we had? And this is just an example to show that we do in fact have that consistency. Here, we're looking at 2 different cases depending on which energy channels we're using from NICER. This is the oval spots. These are 2 ovals. This is a fairly complex model. And we see that we're getting something which is at about the 1.5 sigma level. So that's not at all inconsistent. These sorts of checks are necessary to ensure that we have reasonable fits. This is where I had my pause for questions. So I'll be happy to pause for a minute or 2 to answer any additional questions that are coming up.
No questions right now.
No questions right now? Very good. Now we're going to talk about...
Oh, there is one.
Okay,
When you do the fit, do you also include intrinsic scatter?
I guess I'm not sure in what sense intrinsic scatter is meant. If intrinsic scatter is meant statistical scatter, then the answer is yes. If the question is about, for example, scattering or interactions of the radiation along the way from the neutron star to us, the answer is also yes. One of the components here is the interstellar absorption, which is one of the fit parameters.
He's mentioning about statistical scatter.
Yes, that's completely taken into account. We know that there's always, because of the statistical scatter, we know that the best fit is not going to be exactly the same as the parameter values that we put in synthetic data. And that's an example. We have something shifted by maybe 1.5 or 1 sigma. That's consistent with expectations.
Okay, no more questions right now.
Okay, now let's move on to talk about the results. Here we have our first representation. We're looking at mass versus radius, and this is consistent with the way that things are usually presented, radius on the horizontal axis. And here we have on the left the mass radius posterior, where the inner bit here contains 68% or 1 sigma of the posterior probability, and the outer one here contains 95.4% or 2 sigma. This is for 2 ovals, this is for 3 ovals. These are independent fits, and as you can see, they're completely consistent with each other. By the way, the color scale is the credibility, so the peak here is the most yellow. We can also look at one-dimensional posteriors, meaning that, as in the standard approach, what we do is we take the full posterior over all the model parameters, all the angles and temperatures, things we don't care about, and project it down to 1 dimension. We have mass, we have radius, and we have distance. And this is, again, the top is the 2 oval model, the bottom is the 3 oval model. Now, a little bit of background here. The nicer data we get comes in energy channels, and the energy channels are 25 and above. What we found, though, in some of our initial analyses is that if we were to use channels all the way down to 25, and if we were to allow ourselves a flat and broad prior on the distance, that the implied distance we get is significantly larger than this known distance with uncertainties. We don't know why that is. There are very specific reasons to think that, at least at that time, the instrumental response was not very well calibrated below about channel 40, whereas above channel 40 it was fine. And so we used channel 40 and above. And here what we see is the prior based on the known distance, and this is the posterior. And this tells you 2 things. One is that the nicer information doesn't give you a lot regarding the distance, and 2, it's at least not being pushed to some unreasonably large value. But the main takeaway here is that we do in fact have consistency again between the 2 oval and the 3 oval model. And the 3 oval, as I said, is formally preferred by a small amount. Here we have bolometric waveforms. This is just based on our best fit, and this is what we have only with the spots. We're not including any background here. Left 2 oval, right 3 oval, again, very consistent with each other. Here the individual dashed lines are the contributions from each of the 2 or each of the 3 ovals that we have. So again, this is very consistent between the 2. Now at this stage, I should mention that our analysis is fully Bayesian. We are comparing models with each other. We're doing parameter estimation in the Bayesian fashion using evidences and so on. And therefore, for those of you who are Bayesian evangelists, let me assure you that we are of the true faith. However, we also have what you might call a degree of moral flexibility in our statistical faith. In particular, as you are aware, in Bayesian statistics, there is no way to talk about a model having a good fit by itself. You can compare two models with each other and determine which is the better fit, but there's really no convincing way to say we have a good fit. But this is kind of important. Remember, I mentioned that the work that Fred Lamb and I have done with colleagues suggests that if you have an acceptable statistical fit, you're not biased. But if you have a terrible statistical fit, you could easily be biased. So one of the things we do about that is we look at comparisons with data using something like chi-squared. Here we have an example of bolometric residuals. We integrate over all of the energy channels and look at the phase and cycles, here with 64 phases. And now we see, here we have the black in histogram form is the data. The red is the full model, including the spots and the background, which is represented here. You see it's a substantial component of the overall counts. And then down at the bottom, we have chi. This is the signed square root of chi-square. It's the data minus the model divided by the square root of the model. The fit is good. We can see that this actually works just fine. There are no giant spikes. There's no particular pattern of residuals. If we go a bit further, we can look at the full set of data. Here we have energy channel from 40 to close to 300. And here we have the phase bin for 32 bins. There are no evident patterns. And the chi-square per degree of freedom is certainly in the acceptable range. But I do want to make clear to those who are Bayesian evangelists how we're using these chi-squares. If the chi-square for the degrees of freedom is terrible, the fit is bad. Something is wrong. The model is incomplete. This would therefore be a warning sign that we cannot take our inferences as necessarily being reasonable. So if it's bad, there's a problem. But what about in a case like this where it's good? We cannot use that to say, oh yes, we have done the model correctly. This is the right model. We cannot say that. It's a one-way test. So this passes the test, but it doesn't prove that we're correct. We also have spot patterns. I mentioned these earlier. The top row is for the 2 oval. The bottom row is for the 3 oval. In the left-hand panels, we see an equal area equatorial projection. This horizontal line at the top represents the observer, or R, colatitude on the surface. And here are the two different spots. On the right-hand side, you see a south polar projection, and it's obvious that at least one, and maybe both of these, are in fact not circular. This is intriguing. It tells us that we do not have a centered dipole pattern. And that's something that might be a bit of a shock, because when we look at textbooks, we are often seeing a centered dipole for a neutron star. But there's no special reason to imagine this will be the case. We have examples in our solar system where the magnetic field is at least significantly offset from the center of the star. And in fact, it probably has substantial multipole contributions. Well, why is this? We can think about millisecond pulsars. Now, pulsars in general, we can think about what is their magnetic field evolution. And until 1992, the standard wisdom is that a pulsar by itself would just have its magnetic field decay. But a critical paper in 92, led by Dipankar Bhattacharyya, demonstrated that in fact this is not so. By itself, the magnetic field is not going to decay on timescales anything like a pulsar lifetime, tens of millions of years. And yet, millisecond pulsars have dipole magnetic moments which are some orders of magnitude less than what you have for a newborn or relatively young pulsar, such as the Crab pulsar. Why is that? It's not just because the field spontaneously decays. Instead, probably it has something to do with the evolution, with the accretion. It's very difficult to know what's happening. There's no reason to imagine it should be simple. At this stage, I'll pause again for any questions before I talk about equation of state implications.
Anyone has any question, please write down in the chat box. Uh, there are two questions. Neutron star atmosphere composition and ionization state and its effect on measured M and R.
Yes, this is a critical thing that we're trying to examine very carefully. Let me address both of those because they're both important with respect to J0030, the pulsar we analyzed in the December papers. In terms of the composition, we believe that the lightest element present is going to float to the top within seconds because the neutron star surface gravity is so substantial. Hydrogen is therefore the best guess, and I'm showing you fits with hydrogen. However, there are cases in which you could imagine that the composition would be dominated by helium based on the history of the pulsar, for example. One of the things that we did is we also did some fits, not as extensive, using a helium atmosphere. And we found that the fit wasn't as good statistically, but more importantly, the answers were peaked at unreasonably high masses. With this in mind, although a full analysis would be better to do this, helium atmospheres are disfavored. In terms of the ionization state, if the atmosphere is cool enough, of course, we worry about partial ionization. And the tables we used have full ionization of hydrogen. However, the temperatures here are on the order of 0.1 keV, so that's like 10 to the 6th Kelvin, where we expect full ionization. So as a result, we do believe that fully ionized hydrogen is a good approach to take for this pulsar.
So how high is unreasonably high, the mass?
So here we're talking about things like a minimum of 2.2 or 2.3 solar masses. It's not to say that this is impossible necessarily, but it's a lot higher than we would expect for a system like this.
Okay. Another question, are there any further consequences of the co-rotating magnetosphere?
One of the things about the magnetosphere, this is in a sense the source of the energy that gives us the X-ray. If we look, for example, at how it is that we're going to get X-rays emitted, then we note that because of the pulsar mechanism, we have very high Lorentz factor electrons and positrons moving around that hit the surface and deposit energy. So this is a way that we can think of the energy being deposited. Another thing we worried about is the prospect that if you have high energy emission, maybe a power law, this could be modulated and it could in fact somehow interfere with what we're looking at for the thermal emission. But further examination suggests that this is irrelevant. We can look at high energies where the power law would be more important, and it has only a minimal role to play compared to the thermal emission at lower energies.
Okay, I have one question. You said that this B field doesn't decay for with respect to this Dipankar's work. Am I correct?
Yes, well, right. So they were careful in their phrasing. What they said is that when they looked at all the evidence, there was no evidence that on a typical pulsar lifetime, the field decayed at all.
Okay. But I know that people work on evolution of magnetic field, right?
Yes, they do. Yes, and go ahead.
Well, yeah, that's like so there is a contradiction between the two, right?
There's a question of time scale. There's also a question of the environment. Because from the theoretical standpoint, it's not easy to see how an isolated pulsar would have its field decay even 100 million years. The millisecond pulsars have probably undergone at least tens and maybe hundreds of millions of years of accretion at different levels. Probably the most popular idea is that something about the accretion manages to change the magnetic dipole moment, and there's disagreement about that. One thing you might imagine, for example, is that the accreting matter somehow buries the magnetic field, but it's highly conducting. It's not easy in a practical sense to be able to keep the field buried? I'd say this is still an open question.
Okay. So thank you. Another question is, what physical properties of neutron star can be extracted from the AMAT diagrams?
From the which diagrams?
This mass radius diagram.
Oh, yeah. Well, that's a bit of a tricky issue. The mass and radius, as Jim indicated in his talk, sometimes people think about this as a mapping, but really what you want to do is say, for the pressure as a function of energy density, what would that imply about mass and radius? And from that, and from neutron star data, you can infer things about the pressure and energy density. What you can't do using this data is figure out the composition. You'd love to do that. You'd love to figure out, are these deconfined quarks or hyperons or whatever, but that you cannot do. People have talked about using information from neutron star cooling to get a different take on that, but this has its own challenges. So really, we're thinking about the equation of state is primarily what we're getting out of this information.
So the last question in this part is, how many nuisance parameters you have to marginalize over while doing the fits?
Depending on our exact model, we're talking about somewhere between 10 and 14.
Okay, thanks. So I think we can move on.
Okay, thank you. Now I'm going to give you a couple of different takes on what contribution the nicer observations have made to our understanding of the equation of state. This is the simple version, and then I'll give you something more extensive in the next slide. One thing that you can do is you can take a parameterized equation of state with some priors and then gradually add information. And the nicer contribution has been substantial, and it's going to become more important. What I mean by this is, if we take, let's say this is the spectral equation of state introduced 10 years ago by Lee Lindblom and favored by the LIGO team, you say, what did we know in terms of the range of pressures at different densities? This is the baryon number density, at nuclear saturation density, and then twice that. We had information prior to the nicer measurements. We had the high mass neutron stars, we had the double neutron star event, and so on. Now we add the nicer observations, and what do? Well, what we're doing over this range is shrinking the middle 90% of the pressure range by somewhere between 10 and 30%. That's already a fairly good return. Something that we're looking forward to is that even just on this pulsar, the exposure time will roughly double by the end of this calendar year compared to the data we analyzed for those papers. So we're certainly going to improve this significantly. And as I will return to in my conclusion slide, we have other pulsars that we're looking at as well. Now, what are you doing with all this? You're trying to incorporate this into full equation of state constraints. The path we're taking, perhaps unsurprisingly, is based on our paper Miller, Cadenci, and Lamb, but other people have their own approaches as well. Now, the longer version. This is a figure that we have in our paper, and I'll take a few minutes to go through it. If we're looking at the log of the pressure versus the log of the number density divided by nuclear saturation, the top row uses that spectral equation of state parameterization. The bottom row is a piecewise polytrope. So they're the same basic idea. And the left panel, we see the prior. The dot dash lines are the full range, 0 to 100% in each number density, and the solid lines are the 5th to 95th percentile. The middle panel shows what happens if we add the nicer data. The dotted lines here correspond to what we had for the 5th to 95th percentile in the priors, and the red dash lines and the colored region correspond to what we now have, 5th to 95th percentile, using nicer. So this is clearly improved, remembering that this is a logarithmic plot, so the change here is actually quite substantial, more than a factor of 2. If we then say we're going to add to that nicer data all of the other astronomical data, then we shrink it even further. Here, the red dashed lines are the same as we had in this middle panel, 5th to 95th percentile. And now these solid lines are what you get for 5th to 95th percentile when you include high mass neutron stars and the tidal deformability of GW 170817. We're really narrowing down, and one indication of that is that although you can see that the priors here are quite different, when you add in all the data, they're starting to converge to each other. If we compare this against the Hebler et al. Equations of state from a few years ago, including Jim Latimer, they have a soft, a medium, and a hard equation of state, and we can see the soft is definitely not favored. So this tells us that we really have made significant progress in our understanding of the cores of neutron stars based on observations critically including NICER. In conclusion then, our first measurements have already tightened equation of state constraints. Now I'll leave up this slide as long as I can, but I want to emphasize that so that you can put this into your own work if you wish, all of our samples, the full posterior with every parameter, but also mass and radius, is publicly available here. We have like 1 million samples each, so you can do with that as you wish. The absolute key, one of my points of emphasis, is the measurements appear reliable as well as precise. If you don't have reliable measurements, it doesn't matter how precise your measurements appear to be, they're not helpful. In addition, the future is bright for neutron star observations using NICER. For this particular pulsar, we're going to roughly double the data set by the end of this year, and by the end of the NICER mission, possibly even triple it. We're also going to look at other pulsars. This pulsar J0437 is expected to give us the best precision measurement, and pulsar J0740 is the one with the highest relatively precise measurement of mass. Although, as Manu Lenars pointed out, you can be arguments, but this is one that we're looking at extensively. So all this combined is going to improve constraints substantially. And I'll just finish with a general perspective. 5 years ago, we did have some information about neutron stars, but now we are getting tremendous info from NICER, and in the future, more and more measurements of gravitational wave tidal deformability. We are in an outstanding time to finally make some progress about the cores of neutron stars and what they imply for nuclear physics. Thank you.
Thank you, Cole. We have a question here. Are you connecting the nuclear equation of state at low density, which is possibly known, with PQCD equation of state at very high density with the NICER data?
We are we're following standard practice in that we are assuming that we know the equation of state below half of nuclear saturation density. And that's typical. You need to make some assumptions. It's fairly well known down there, and it doesn't have a big impact on either the mass or the radius. As far as the very high density equation of state, the thing, for example, that gives you asymptotically that the speed of sound is the speed of light over the square root of 3, we're not trying to connect that in part because if you look in detail, the density at which that asymptotic limit holds, it could be tens, hundreds, thousands, millions of times nuclear density. And so we're electing not to do that. There are groups that have tried that approach, however.
Okay. Here is another question about the B field. Can we test observationally using radio pulsar data if B field in pulsars decay after some nominal assumptions? And has this been done in literature?
In terms of the testing of the decay, indeed, this is something that I was mentioning with respect to Dipankar Bhattacharya's work in 1992. The wisdom had been that the pulsar fields appeared to decay, and for reasons that would be a little extensive to go into, it turns out that the interpretation of the data was not correct. Essentially what you do is you want to look at reliable estimates of the age of pulsars as a group and reliable estimates of the magnetic fields of pulsars as a group. And there's no apparent correlation. For an individual pulsar, the time scale is too low. So it's a statistical statement. It's not a proof that there's no decay, but there's no evidence in favor of such a thing over at least tens of millions of years.
Okay. So what other aspects of neutron star can we expect to learn from NICER besides radius? Say B field evolution, non-H atmosphere composition, transients, etc.
Yes, we are certainly going to be able to learn more about the magnetic field configuration indirectly. We're looking at X-ray spot patterns, but to the degree these are correlated with the magnetic field, we have that information. For composition, yes. As we do more and more extensive testing, we can, for example, compare the fit with a pure hydrogen atmosphere or a pure helium atmosphere. And if one of them is strongly preferred, that will tell us something about the composition. And that in turn, if it's helium, will tell us something about the evolution of the neutron star itself.
Any hotspot or neutron star in the binary system?
Yes, well, we're certainly looking for that. For example, the one I mentioned here, this JO437, this is a binary system, and there have been XMM observations, not enough data to say much, but it's clear that there are X-ray modulations which are consistent with there being hotspots.
There was a question, any preliminary result on J0740 plus 66 or other pulses with independent mass measurement that you can share?
We certainly have preliminary information. I can't share it though, sorry.
Okay. So how good a radius measurement we hope for NICER at the end? For example, 5% with 3 sigma?
Not at 3 sigma. I'd say that it's realistic, even conservative, to say that for at least one of these, we're going to have 5% at 1 sigma. And I think that 4% at 1 sigma is reasonable.
Okay. So any more question to call? We have one, okay, Jim wants to comment on the PQCD question.
Yes.
Yeah, please go on.
Go ahead, Jim.
I can't find him online.
There we go.
Yeah.
Okay.
Yeah.
So the PQCD inferences are valid down to a density of about 40 or 50 times the saturation density. So it's not thousands or millions, I think. But in any case, I think the constraints of achieving a certain maximum mass and causality are far more important than PQCD at this point, because those two constraints already direct us along a line that extended naturally merges into PQCD, given that it's such a high density. There's a wide range of the way you could do that interpolation.
Okay. So any comment from Cole on this? Okay. So we move on to the next question. This is from YouTube. What are the precisions one can measure about this mass and radius from future NICER observation, and how do they compare to the estimates from gravitational wave detectors?
And the estimates, as I mentioned, I think that ultimately we're going to get better than 5% and maybe 4%. That's with all the data and analyzing and better understanding of systematic errors. As far as the gravitational wave estimates, one thing to remember is that there was no tidal deformability measured for GW 170817. In that sense, and if you connect it to the radius, there's an upper limit. There are other things you can put in, other additional assumptions, which can give you a lower limit and an upper limit. These, however, end up being a bit more model dependent.
Any more question?
So if we're talking about later observations, you know, in the 5 or 10 year level, when, for example, LIGO India is going to start making critical contributions, then there may come a stage where we can actually measure the tidal deformability. And then it's going to be quite comparable to the precisions we get with NICER.
Okay. Any more questions for the speakers? No? Okay. I have one naive question. When these tidal deformability calculations are done, so they are done for a particular mass, like 1.4 solar mass. Is there a reason for that?
For GW 170817, this is the best estimate. If you happen to have neutron stars that are equal in mass, then they're at about 1.36 solar masses each. But another thing which Jim alluded to is that there are significant correlations one expects between the tidal deformability and the mass. So when you look at this binary tidal deformability that he mentioned, if you fold that in, you can get some greater precision than if you assume that they're totally uncorrelated between masses.
So thank you, Cole, and thank you, Jim, for the wonderful talks. So let us thank them from all of us.